Yep.
Hold on, wait, let me give you 20. Let me give you 20. I'm me. Okay. So again, we're on chapter 45. We started filming late, so we just talked about this, what we call all the different phases of cosmic evolution. Starting with particles in the early universe, atoms that came together in big groups to form our first galaxies, inside which formed stars. Around the stars formed planets. On the planets, we know there was chemical evolution, chemicals reacting with one another to form more and more complex things. We think perhaps some of those chemicals came together to make the first living things, simple bacteria, which got more and more and more diverse and complex through evolution, biological evolution. And eventually formed us. We formed cultures. Cultural evolution means more and more complicated cultures, more and more complicated working together, building more and more complicated tools, and eventually coming up with radio telescopes that could communicate across galaxies and see things far out, and spacecraft that we could launch off our planet. That took a long time. Do y'all know how long it took to get from there to where we are now?
14 billion years.
About 13.6, 13.7 billion years. Let's talk a little bit about the chemical evolution. We know on the Earth that chemical evolution happened. This is one of the experiments that showed how easily it occurs. It's the Miller-Urey experiment. Does anyone remember it from your regular biology studies?
Oh yeah.
Kind of.
What happened was these guys, Miller and Urey, they figured out the sorts of molecules that were present on early Earth. And you can figure that out by busting open many billion-year-old rocks and seeing what gases come out of them. Those are the gases that were around when the rocks first formed. They're held within the rocks for eons. And these guys figured out what those gases were, and they said, let's put them all together in a chamber and give them some energy, little electric sparks, and see if those things become anything else. And they ran it through this condenser where it cooled them off and made them liquid, and then they'd boil it back, and it would go around and around this container. Every time it fell through here, it would get sparked to give it some energy. And after a week or so, they sampled the chemicals that were in there. And you know what they found? They found really complicated molecules. They found proteins, amino acids. They found nucleotides. The nucleotides that help make up DNA. They found fats and lipids, the same lipids that you find in the cell membranes of cells.
Where? Yeah.
What's that?
Where do you find that again?
In this contraption that they built, where they took these simple molecules that are found in early Earth's atmosphere, water and methane and ammonia and hydrogen. They know those were present in early Earth's atmosphere. They know that from opening up old rocks. And they let those things combine in this experiment they set up in their lab. I don't know where they were when they were doing this experiment. But anyway, when you suction out this material that's circulating through here and examine it, you find all these complicated organic molecules. After just a couple of weeks of letting these things bash into one another. You see, molecules, when they hit one another, it's not like when people hit one another. If people hit one another, they just bounce off. If you throw two balls against one another, they'll just bounce off. But if you hit two atoms together at a hard enough speed, they'll stick together and form larger molecules. And that's exactly what we see. You want to see video footage of the experiment?
Yeah.
Now, how did the molecules of life arise?
This is Carl Sagan. Let's turn that back over so you can see him.
Arise.
That's the guy that wrote that book I was reading from.
In a laboratory at Cornell University, we mix together the gases and waters of the primitive Earth, supply some energy, and see if we can make the stuff of life. But what was the early atmosphere made of? Ordinary air? If we start with our present atmosphere, the experiment is a dismal failure. Instead of making proteins and nucleic acids, all we make is smog, a backward step. Why doesn't such an experiment work? Because the air of today contains molecular oxygen. But oxygen is made by plants. It's pretty obvious that there were no plants before the origin of life. We mustn't use oxygen in our experiments because there wasn't any oxygen in the early atmosphere. This is perfectly reasonable because the cosmos is made mostly of hydrogen, which gobbles oxygen up. The Earth's low gravity has allowed most of our original hydrogen gas to trickle away to space. There's almost none left. But 4 billion years ago, our atmosphere was full of hydrogen-rich gases, methane, ammonia, water vapor. These are the gases we should use. Taking great care to ensure the purity of these gases, my colleague, Bishan Kari, pumps them from their holding flasks. An experiment like this was first performed by Stanley Miller and Harold Urey in the 1950s. The starting gases are now introduced into a large reaction vessel. We could shine ultraviolet light on this mixture, simulating the early sun. But in this experiment, the gases will be sparked, as the primitive atmosphere was, by early lightning. After only a few hours, the interior of the reaction vessel becomes streaked with a strange brown pigment, a rich collection of complex organic molecules, including the building blocks of the proteins and the nucleic acids. Under the right conditions, these building blocks assemble themselves into molecules resembling little proteins and little nucleic acids. These nucleic acids can even make identical copies of themselves. In this vessel are the notes of the music of life, although not yet the music itself. Now,
Okay, let me stop it there. That was from that show Cosmos. Do you remember that, Amir?
Yeah.
Did you watch that whole series?
Yeah, man.
I don't get what goes on inside of the little sphere.
The molecules are hitting one another, sticking to one another to form bigger molecules. And those big molecules take the shapes of these organic molecules that you learn about in biology. So organic molecules are made from this stuff originally. It's the same molecules you find in living things. They have had these experiments going for 60 years, 70 years now, where they just keep bashing stuff together in these vessels, and they've come up with things that look just like cells and behave like cells and take in material and grow, and when they get big enough, they divide. They're very close to making a cell from scratch in a lab. That'll happen sometime soon. And then when it does, we'll have the first living thing ever made on its own since the first living things came about billions of years ago. It'll be a very exciting, you'll read about that sometime in the next couple decades. That's coming. And it sheds some light on how the first living things probably arrived here on Earth. Now, is this kind of thing, this chemical evolution, is it happening anywhere else, or did it just happen on Earth? We have clues that it's actually happening somewhere else.
No.
What are those clues? Meteorites. Meteorites come in from deep space, way out there in the Oort cloud, or the Kuiper belt, and they slam into Earth, and we pick them up. They're easiest to find on the ice of Antarctica or Greenland, because it's all white out there, and you'll just see this black rock. It might have been sitting there for thousands of years. You drive by it, and there it is, and you pick it up, and if you examine it, in those meteorites, we find the same stuff. The same large molecules, amino acids, nucleotides, complex sugars, lipids, the molecules that make up living things. So this is obviously not just happening on Earth. It's happening on other planets, and it's happening out there in space. These molecules are hitting one another and sticking together, making bigger molecules. Isn't that cool?
Yes.
So we think that probably with that evidence that it can happen on Earth, it does happen in space. Maybe there should be life on other planets elsewhere. This is something very cool. I don't know if you heard about this, but this is a microscopic picture taken from a meteorite called ALH 84001. It's a meteorite that came from Mars. We know it's Martian rock because we've had rovers up there examining Martian rock, and we know exactly what Martian rock is like. Santana, are you with me? Santana! This is good stuff. And those Martian rocks, one of them, something obviously hit Mars, blew pieces of material off of it. They floated through space, hit the Earth. We opened up that Martian meteorite and we saw that. You know what that looks like to a lot of biologists?
Bacteria.
That looks like a bacteria.
Score.
It looks like bacteria living in a long strand of many bacterial cells together. And if that is true, if that's fossilized bacteria, that means there was life on Mars at one time. Now, some scientists look at that and go, nah, I don't think it's bacteria. And other scientists look at it and go, yeah, that's bacteria.
Is this a zone picture?
That is a microscopic, that's a picture taken with a microscope of the inside of a Martian meteorite. But that's kind of a famous picture and a famous meteorite, and so there may have been life on Mars at one point.
Like, are we talking microscopic?
Microscopic. This is microscopic bacteria. So what scientists want to do is they want to send machines there that can dig up rocks on Mars and look at it microscopically and see if there's more of that. And do other tests on it and such to see if there used to be living things there. Maybe there used to be living things there and they're all extinct now. Or maybe there used to be living things there and they're still there. Deep down in the rocks. Wouldn't that be cool? There might be life on Mars. Y'all know who this is?
Darwin.
Charles Darwin.
Score.
Yeah, as an old man. And he said that, or he showed through his theory of natural selection, which we're studying in biology now, he showed that if you get one single cell form, and that cell can multiply, then it can change through mutations and other ways into new forms. And you can have this huge biological diversity develop, but all you need is one cell to start with. So perhaps this is what happened on Earth. We got a single cell, it multiplied, and through mutations changed to other forms, and some of those forms were selected for, and there became more and more of those forms. Evolution by natural selection took over and made all the different forms we have on the planet today. Of course, cultural evolution starts when you get humans and human culture. And science leads to better and better machines, better and better inventions, better and better tools. The tools have gotten incredible. What do you think a caveman would say about that?
He would smash it.
I can't even explain. I can't even begin to explain that.
I mean, this is unbelievable. Not even a caveman. What do you think a guy in the 1970s would say about this?
Yeah, no,
I mean, that was science fiction. As a matter of fact, it really was science fiction because it was in Star Trek, the show. They had these little things and they talk on them, and we were like, no way, you can talk to a guy on the ship with that? There's no way.
I was gonna say, like, whenever I try to talk to my grandparents about whenever they try to figure out anything about iPhones, they can't I don't. Is there something about their brain that
electronics
to
Yeah, they grow up with it. They don't understand it. Yeah.
Even if you try to sit down with them, they just won't. They can't.
They don't. Yeah.
I don't understand how it works.
Yeah.
Comprehend.
But they didn't grow up with them, and you learn best when you're young. And you learn how wires go together and all that stuff when you're young. And if you didn't learn it when you're young, it's hard to pick it up later. It's kind of like learning a new language. It's hard to teach an adult Spanish, but kids pick it up real quickly and easily. They hear it all the time. Kids can get
We'll
it.
have something that we won't know.
There will be something that comes up that'll just your grandkids will be telling you about, and you'll be like, I don't get it. I don't know how to do it. Part of it is them not
There is another
wanting to
perspective by which to
understand.
measure human endeavors.
Yeah.
Let me tell you a story about the beginning. Some 15 billion years ago, our universe began. The mightiest explosion of all time. The universe expanded, cooled, and darkened. Energy condensed into matter, mostly hydrogen atoms. And these atoms accumulated into vast clouds, rushing away from each
Andy,
other.
watch this. This is
that
great.
would one day become the galaxies.
This is the same song from the Planets one.
Within these galaxies, the first generation of stars was born, kindling the energy hidden in matter, flooding the cosmos with light. Hydrogen atoms had made suns and starlight. There were in those times no planets to receive the light, and no living creatures to admire the radiance of the heavens. But deep in the stellar furnaces, nuclear fusion was creating the heavier atoms, carbon and oxygen, silicon and iron. These elements, the ash left by hydrogen, were the raw materials from which planets and life would later arise. At first, the heavy elements were trapped in the hearts of the stars, but massive stars soon exhausted their fuel and in their death throes returned most of their substance back into space. The interstellar gas became enriched in heavy elements. In the Milky Way galaxy, the matter of the cosmos was recycled into new generations of stars, now rich in heavy atoms, a legacy from their stellar ancestors. And in the cold of interstellar space, great turbulent clouds were gathered by gravity and stirred by starlight. In their depths, the heavy atoms condensed into grains of rocky dust and ice and complex carbon-based molecules. In accordance with the laws of physics and chemistry, hydrogen atoms had brought forth the stuff of life. In other clouds, more massive aggregates of gas and dust formed later generations of stars. As As new stars were formed, tiny condensations of matter accreted near them, inconspicuous motes of rock and metal, ice and gas that would become the planets. And on these worlds, as in interstellar clouds, organic molecules formed, made of atoms that had been cooked inside the stars. In the tide pools and oceans of many worlds, molecules were destroyed by sunlight and assembled by chemistry. One day, among these natural experiments, a molecule arose that quite by accident was able to make crude copies of itself. As time passed, self-replication became more accurate. Those molecules that copy better produced more copies. Natural selection was underway. Elaborate molecular machines had evolved. Slowly, imperceptibly, life had begun. Collections of organic molecules evolved into one-celled organisms. These produced multi-celled colonies. Their various parts became specialized organs. Some colonies attached themselves to the sea floor. Others swam freely. Eyes evolved, and now the cosmos could see. Living things moved on to colonize the land. The reptiles held sway for a time, but they gave way to small, warm-blooded creatures with bigger brains, who developed dexterity and curiosity about their environment. They learned to use tools and fire and language. Star stuff, the ash of stellar alchemy, that emerged into consciousness.
That's how you go from stars to people.
That's insane.
In 4 minutes.
Wow.
The other way. Open up.
But there is another perspective by which to measure human endeavors.
I want to watch that last. He goes from the first cells, the first molecules in about 40 seconds to humans. And this is an accurate representation.
Collections of organic molecules evolved into one-celled organisms. These produced multi-celled colonies. Their various parts became specialized organs. Some colonies attached themselves to the sea floor. Others swam freely. Eyes evolved, and now the cosmos could see. Living things moved on to colonize the land. The reptiles held sway for a time, but they gave way to small, warm-blooded creatures with bigger brains, who developed dexterity and curiosity about their environment. They learned to use tools and fire and language. Star stuff, the ash of stellar alchemy, had emerged into consciousness.
Cool. Good. Good art there. All right, so read the section, the chapter 45. We got one more.